Uh, Welcome Electronics 2018 22nd International Conference. This is session 6A. My name is Abdullah Tola, Professor Dr. Abdullah Tola from Pamukkale University, Turkey. I am the chairperson. We have 6 presentations here in this session. Total time is 90 minutes, so each presenter have only 50 minutes. Right now, 5 of them is here. The other person is registered and came yesterday, so we will expect him again. So let's start the first presentation. The study of transient electromagnetic response of high resistivity goafs and its application. The presenter name is Jun Lo. You have only 15 minutes, including questions and answer session, okay?
Thank you, Chairman. Good morning, everyone. My name is Lo Jun. The presentation title is the study on transient electromagnetic response of high resistivity goaf and its application. So it's mainly focused on the goaf to detect the goaf of maybe manuals. As you see, this paper is mainly accomplished by China University of Mining and Technology, and I'm not one of those. So the outline is organized as 4 parts. First, I will introduce the principle of TEM. TEM represents the transient electromagnetic method for detecting high resistivity goafs, and we will do some numerical calculation and physical modeling, and finally comes the conclusion. This is the principle of TEM to detecting high or low resistivity goaf. It means in the this is the model. During the on time, the transmitter generate the primary field. Then if there is a goaf in this area, so there will be a AD. The AD will be generated, and the AD will generate the second field. So the second field can be received by the receiver. Through some process, we can get the response through TEM. Traditionally, the TEM is used to detect low resistivity goaf. So, so this paper will mainly focus on how to detect high resistivity goaf. That's the main part. Part 2 is about the numerical calculation. This is 2 cases. One is for the low resistivity, and one is for the high resistivity. And this is the response of TEM. We can see that in the low resistivity case, we can see that the changes can be it's obvious based on different valued depths. But we can see in the high resistance, the changes is very low. Also, both cases we can see that the response is very weak. So how can we get some useful information from these 2 cases from the results of the response of TEM? We used subtracting. From these 2 results, we subtract the background field, so we can get the figures on the right side. So with that, we can see that both the The changes of both cases, low resistivity and high resistivity, we can get a relatively obvious changes, which is based on the buried depths. So this is a transfer. These two cases of numerical calculation is based on one dimension. So we will see it's 3-dimensional. This is the 3-dimensional model. Also, these two cases, the transmitter is 600 multiplied 600 meters, and this is the goaf. The size of the goaf is 100 meters plus multiply 100 multiply 20 meters. So we can see here the response of TEM of these two cases and the background field. This is the detect response result. Also, we use subtracting background field. This is the result, and we can get this figure. We can see that in these cases, we can see that on obvious changes through the time represent the depths, which we can see the high resistance and the low resistance. The high resistance, the change of the high resistance is relatively low than the low resistance. In part 2, we will discuss the numerical calculation. So in part 3, we will focus on the physical modeling. Physical modeling, this is the physical modeling, the top view and the side view. We also use the transmitting coils is 50 centimeters multiplied 50 centimeters. There are many receiving points along this line, so we can get the response through TEM of the high resistivity. The high resistivity and the low resistivity, the difference is that in actual is that if a goaf is full filled with water, then it belongs to the low resistivity case. But if the goaf is empty, so it belongs to the high resistivity. This is the physical modeling, and we will get a physical actual testing result, which uses 5 terms. In each term, there are 30 measurements along the distance, which means that there are 30 receiving points. This is the response, which is the acquired voltage. So after we get this data, we've done a transfer from voltage to resistivity and from time to depth, so that we can get this picture. This is the measured induced voltage, and through these two functions, equations, we can get something like this. In this picture, we can see that the high resistivity, here we can get the high resistivity Turner magnetic cavity. This means that through the TEM method, we can detect high resistivity of goaf. That's what we can get from this experiment. So this is the physical model, and this is the actual result we got. We can see that tunnel, and we can see this is the hollow. So we can get here. So I think it's matched. The actual result matched the models very well. Here comes the conclusions. So we've done numerical calculation of one-dimensional and three-dimensional of the of the model, and we can see that the TEM method of high resistivity of goafs are weaker than that of low resistivity vehicle, but we can use this method to detect high resistivity goaf. Another conclusion is that physical modeling results show that high resistivity elements objects can be effectively detected. So it appears that it appears that this research can have has a wide application in exploring the Earth. Thank you.
Thank you very much. Is there any questions? Comment? No? Okay, thank you very much.
Thank you.
Our next speaker is Janis Zakivs. I'm sorry about the pronunciation. QZS inverter as synchro converter in small scale microgrid. The speech of the name of the speech. We have 15 minutes.
Okay.
Including the question section.
So, good morning, dear colleagues. My name is Jānis Zakis, and I am from Riga Technical University from Latvia. The title of my presentation is Quasi-Z-source inverter as synchro inverter in small-scale microgrid. I am representing a group of authors, and since here are different fields in electronics, and not only during my presentation I will tell more what does it mean quasi-Z-source inverter, what is synchro inverter, what those strange names mean. But okay, let's start with motivation. Everything is about power generation or distributed power generation. So not many years ago, power generation was centralized. What does it mean? It means that basically electric energy was made by big synchronous generators in whether hydropower plants or combined heat and power stations. Today the situation is a little bit different. Every one of us, we can install PV panel or small scale wind turbine in our house. We can add microinverter and we can sell electricity to grid or contribute somehow energy system. But those small microinverters are not very reliable because they cannot work in the grid if there is no big synchronous generator which can keep the voltage level and frequency. That's why there are additional requirements for those microinverters. First of all, they should flexibly pre-regulate input voltage. For example, if the sun irradiation is not in the rated level. Also, for distributed power generation, microinverter should work in grid connected mode and also in islanding mode. And next I would like to show the diagram, which consists of so here is grid, and in parallel with grid is, for example, microinverter and other system, which I will tell in a couple of minutes. For example, if grid fails or synchronous generator in the grid fails, so it means there is no element which can control voltage or frequency. So, and our proposal is to make virtual synchronous generator, which consists of quasi-Z source network, single phase inverter, filter. And also in the same system are microinverters and primary energy source like PV panel. So the main thing, if there is no basic energy source, then power system can collapse, because only microinverters cannot keep all the network parameters. So we propose to use quasi-Z source network, which I will describe in the next slides, which is coupled with single phase inverter. Single phase inverter in this case will work as synchro inverter. What does it mean? It means that inverter is controlled with the same mathematical function or control system which has this the same like synchronous generator. Also in the DC link can be added some battery, but it is not mandatory. And since the primary voltage source is not very stable, so usually this is pre-regulated in some DC-DC converter in order to keep DC link voltage in the rated level. Now I would like to tell more about what does it mean quasi-Z source inverter. This inverter is one of special converters from impedance source converter family, which was discovered 15 years ago. It started with Z source inverter, and this is quasi-Z source. This is a modified version. How does it work? So this is quasi-Z source network, which is coupled with conventional voltage source inverter. In power transmission mode from primary side to secondary side, diagonal transistors are employed, so everything works as conventional voltage source inverter. But in case if input voltage decrease below rated value, we need to step up voltage, and this is done with special switching state, which is not allowed in traditional voltage source inverters when both transistors of one phase leg are conducting. Usually it can make a short circuit of DC link capacitor, but in this case it is absolutely normal because of this special connection. Here we can see equivalent circuit, so we can see that capacitors are in series with inductors, which actually limit current growth. So, and in this way we can re-regulate input voltage by storing magnetic energy, which in turn provide voltage boost on the primary winding of the transformer, and we can increase input voltage. So that's how we can keep stable DC link voltage. And then besides to that, also this inverter works as synchro inverter and mimics synchronous generator in the grid. Okay, I will not talk about the quasi-Z source inverter because about operation modes, basic modes I told, but I would like to turn your attention to simulation results. So here is grid voltage, here is grid current, here is microinverter, and here is output current of synchro inverter. Just let's go back and see once more here in the picture. So here is grid current, this is microinverter current, here goes, and here synchro inverter current. So, and there were several cases when load demand is increasing, when microinverter is turning on, and when load demand is reducing. And let's see, let's zoom all of those borderlines. First of all, when load demand is increasing, so we can see that here is grid voltage, grid current, microinverter is not working at this moment, and synchroinverter current. So we can see if we add additional load, so the current is bigger, and the same is in the grid current. If we look next step, when we add microinverter in parallel with synchroinverter, then the sum of microinverter and synchroinverter is the grid current. And we also see that grid voltage is in the same level. And the last case, when load demand is reducing, and so here still microinverter is working and helps to synchroinverter, but since the load drops, also grid current drops, and also here the sum of those both is grid current. Okay, very shortly, that's all about the simulation results, and the main conclusions are: the functionality of proposed microgrid was verified where one of inverters operated in virtual synchronous generator mode, and other inverters could have been involved in those voltage and frequency regulations, thus maintain total power balance. The output voltage control as well as harmonic compensation of the current control of the synchroinverter defines the quality of the output voltage in steady state mode. At the same time, internal microinverter control systems mostly define the quality of transient process during the connection and disconnection. Most complicated part in the control strategy for microgrid consists in reference power generation and distribution of currents between synchroinverter and microinverter was weakest part of the system. So thank you very much, and if you are interested in more technical details, you can look in the papers, in my paper, because I made my presentation very general in order to make a global understanding, but more about synchroinverter and its control you can find in my paper. Thank you very much.
Thank you. Any questions? Any comments? Contributions? Okay, thank you very much again.
Thank you.
The next speaker is Petr Zajic from Czech Republic. The name of the presentation is Shielding Protection Compression for Security Cameras lenses. We have 15 minutes, including question section.
Good morning, ladies and gentlemen. Thank you for introduction. My name is Petr Zajic, and I'm from here of Tomáš Bati University in Zlín, Faculty of Applied Informatics from Czech Republic, and I will present you the paper of my colleague Stanislav Kovář, who is a main researcher of this topic, and it's called Shielding Protection Comparison for Security Camera Lenses. I would like to explain the situation first, because I'm a substitution person for presentation, because my colleagues wasn't able to attend because he is doing his research in Netherlands today. Okay, and I want to introduce myself, of course, because I'm not familiar with this topic too much as my colleague, but I'm a researcher in the topic of cryptography. So I would like to apologize a little bit for reading it, because I don't want to miss the transfer of the main topic of the research from my colleague. Thank you. And my speech is divided into main 4 areas, as you can see in the presentation. It will be about introduction, experiment part, and results, and some conclusion. The second area, which will be about experimental phase, explains, followed by research. to the introduction. My presentation aims at the suitable shield, searching for security cameras, especially comparison of different kind of hole shape, because there is a lot of publication with various results and conclusions. It could be some misleading. The question is why I choose this topic. I'm from the faculty which focuses on security devices, and one of the devices are security cameras. They are really spread in the field of the security topic. Currently, the number of cameras increases, and they represent the critical factor in the security field. However, these devices are really sensitive to the electromagnetic field, especially the light-sensitive elements such as CCD and CMOS sensors. This finding mentioned, for example, in Martin Pospišilik publication, which is his colleague, and it's mentioned on the topic. Unfortunately, the shield design is not a simple matter because of the objective presence. The first idea of how to solve this problem is interestingly conducting polymers, ICPs. However, they do not research desired results. Therefore, the authors choose the traditional way using a metallic material with the holes. As you can see on the experimental files, there is the mentioned metallic material with the holes to shield the. Now, let's say something about the experiment. The experiment was performed using two softwares, namely CST Microwave Studio and Wolfram Mathematica for the calculations. CAD Microwave Studio disposes of a function called macro, which used Visual Basic for application, programming language based on Visual Basic, of course. This macro allows offering another solution how to create, set or run the project. The experiment described here works with macro, but another software activates this function. CST Studio serves only as a tool for electromagnetic calculations. Conversely, Wolfram Mathematic triggers algorithms for shape design and creates holes. As you can see from the experiment part, grid dimension is 50 by 50 by 1 millimeters. Circular hole's diameter is 5 millimeters with thickness 1 millimeters. It was like honeycomb shape. Okay, there's the research part that leads me on the most interesting part, I guess. The results. The first figure illustrates the electric field detected by a probe behind of the shield with circular holes. This variant reduces electrical field passage by 35 decibels by volts by meter. The shielding effectiveness was calculated according to the IEEE standards, ratio of input to output, definition of shielding effectiveness, as you can see on the presentation. Another part of results, the second figure illustrates the electric field detected by a probe behind of the shield with rectangular holes. This variant research reaches worse result than the one mentioned before. The difference is approximately 5 to 7 decibels voltage by meter. However, the visibility is better. Therefore, it is more suitable for objective protection based on the results. Another results are the last figure illustrated the electric field detected by a probe behind a shield with honeycomb holes. This variant recorded the worst results, but in comparison with rectangular holes, the differences are negligible. The visibility is better than the shield with circular holes, but the worst than the one with rectangular holes. This variant looks like the least suitable for lens protection purposes. And as a conclusion, that's the end of my presentation. Now let me sum the key points of my presentation. Firstly, electromagnetic interference has become the serious problem for all electronic and electrical devices, especially for security cameras, where the great emphasis is placed on reliability. Secondly, the work is based on the knowledge mentioned in world-known publications, which are applied to a new research field. Finally, future work should focus on visibility because the designed solution is not the best one for cameras and can be improved. There are some references, and that's all from me. If you have some questions, please kindly ask you forward to my colleague, which is responsible for this topic, and he will be able to ask you all questions, and he will be glad for that.
Any question?
Okay. Thank you for the attention, and there is the contact to my colleague, and of course more details are in the topic and paper.
Any question? I have a question. Are you planning to go to repeat the experiment with different shape?
I think yes, because I've already seen his research, and it was last week where he's trying another shapes already. Yes,
already.
And it will be invited to another paper and another research, of course.
Yes, please.
The question is, according to European Union law, each equipment, for example, camera, has to be tested according to standard
Of course.
for electromagnetic field immunity.
Yes,
for
of course.
field. Have you equipped any camera with this shielding and tested
yes.
for the agreement with this? Tested according
Yes,
to
I can ask you your question. I think my colleague is not. He has not already equipped real camera. It's about simulation part, but we have in our faculty we have all necessary equipment to test it according to standard semi-annealing chamber and ATC. Okay, it will be tested, of course.
Yes. More
Any
questions? More question? Okay, thank you very much.
Thank you very much too.
Okay. The next presentation is about planar inductor for biological experimentation in pulsed magnetic fields. The presenter is Sebastians Kurchovskis. I'm sorry, the pronunciation. Please. You have 15 minutes again.
Okay.
The previous speakers finished earlier than expected, but
So, good morning. My name is Sebastianas Kurchovskis, and in today's presentation I will present you planar inductor for biological experimentation in pulsed magnetic field. So let's start our presentation, and in the first slide I will gladly present you and introduce you all to the world of magnetophore mobilization and show you briefly how it works. So we basically have pulsed power system, we have the coil, and we have the impermeable molecules, and we have also living cells. We place it all together. Then we have the pulsed magnetic field. We have induced electric field, and we have and we can receive temporary nanopores. After the treatment, the initial impermeable molecules stay inside the cell. So basically, this system could be briefly used in engineering, the cancer tumor treatment, DNA transfer or transformation, and many other also spheres. Yeah. So in the second slide, as it was said before that, with the temporary nanopores, we can see that in the first picture of the cells, we have the high magnetic field in inductor, and we have commercially available cuvettes. And in the second picture, we can see the magnetic field this distribution in the cuvette. And now we can see the multi-layer planar in inductor. The basic principle of it, and each inductor has its own generator, and different substrates are being used to cover overheating during the experimental process, because as we know, we need to maintain the stable temperature during the experimental part. At this slide, we can see the finite element method analysis. We can see the axis of we can see the treatment area, the panel inductor, and the magnetic field lines. Everything was made with the coral. Well, and we are in this part we are raising everything to 1 Tesla. We are available. We can in the theoretical part we can raise it until 10 Teslas, but right here we will use only until 1. And also we can see in the other graph we can see how the system responds during the experiment. We usually receive a lot of heat, so we are using different substrates just to cover the heat loss. Yeah. So basically, we are working until 30 with our system, and if we will use, the graph shows with different substrates how the heat works during all the experiments. Now we can see the pulsed magnetic field generator. We have 4 different voltage sources. We have the planar coil numbers can be a lot more. It's only here we show only 4, but we can increase the number of planar coils. We have the MOSFET also for faster discharge. And in our system we use this kind of topology. And later on, regarding the conclusions, the proposed multi-layer planar inductor geometry consists of 4 planar inductors with an internal diameter of 3 millimeter and outer diameter of 7 millimeter can generate under 1 Tesla amplitude pulsed magnetic field. For the better treatment area heat exchange characteristic, instead of the textulite, the aluminum oxide substrates are recommended to increase the heat transfer, because the aluminum works at its best. The warm-up of the multi-layer impulse inductor of the aluminum oxide is 40 Celsius lower than the prototype of the textulite, which can have a positive effect on biological research. The proposed planar inductor design ensures stability of the geometric parameters of the inductor due to the increased stiffness of the structure. So that was the short introduction. Thank you all for the attention. The brief introduction could be also seen at our paperwork. So if you have some more powerful questions, you can also read there. There's all the answers there. So thank you all for your attention.
Any questions? Contribution? No? Okay,
Thank you so
very
much.
Thank you very much. Okay, we are going very well in terms of time. The next speaker from Poland, Leszek Nowosilski. The title of presentation is Angular Dispersion Modeling for 5G Wireless Link with Directional Antennas. Sir, you have again 15 minutes for presentation.
Good morning, my name is Leszek Nowosilski. I come from Poland, from Military Institute of Technology. My person and my colleagues wrote article. The title is Angular Dispersion Modeling for 5G wireless link with directional antennas. The agenda of my presentation: introduction, three-dimensional propagation model, angular dispersion, algorithm for simulation study, assumption for simulation studies, and simulation results. And then I tell some word about the conclusions. Introduction. The development of modern wireless communication is heading towards fifth generation system. The use of spatial multiplexing is one of the essential features of these systems. A practical implementation of this multiplexing method is based on antenna arrays that allow the use of multi-output techniques. Active phase antenna 2. A problem of ensuring of a compatible cooperation of various links of individual fifth generation systems users is a consequence of the use of multi-beam selective antenna systems. Hence, an evaluation of a power angular spectrum and RMS angle spread of the received signal as a function of radiation reception directions and bandwidth of antenna patterns is important to determine the conditions of non-interference operating 5G system components. All methods that allow the power angular spread assessment can be divided into empirical, geometric, and simulation methods. The first group uses standard distributions, for example, Laplacian or Gaussian, to describe the dispersion of reception angle. In this case, distribution parameters are determined on the basis of statistical relationship between the parameters describing dispersions in time and angle domain. The main disadvantage of these models is the independence of statistical power distributions from the distance between the transmitter and receiver position. Geometric models that consider a mutual location of objects and areas of scattering occurrence don't have this disadvantage. However, in this case, knowledge of the spatial structure of the propagation environment is required. Hence, the obtained assessment of the scattering is the reception angle is closely related to the spatial structure of an analyzed propagation scenario. A statistical result of power angular spread is provided by simulation models, which are defined by the third generation project and Wiener projects. the models determined average values and statistic of parameters for all components of the received signal are input data. However, in this case, the parameters properties are independent of the distance between the transmitter and receiver position, which is a significant weakness of these models. Additionally, the models used so far assumed the omnidirectional antenna patterns. Thus, the models cannot be used to map propagation phenomena into various links with the directional antennas. In our paper, we show the possibility of using the multi-ellipsoid propagation model, the abbreviation is MPM, to determine the power angular spread statistics as a function of the antenna parameters such as gain, antenna gain, half power bandwidth, and maximum radiation reception directions. The originality of the presented solution results from the use of mapping which based on one-dimensional characteristics such as a power delay profile. These parameters, these characteristics comes from empirical measurements. Or power delay spectrum ensures the determination of probable location of the scattering elements in 3D. The use of literature measurement data to determine the parameters of the multi-ellipsoid structures and antenna pattern. Therefore, the geometrical structure of the model is also closely related to the environment type and empirical data. On this picture, you can see the structure of the multi-elliptical propagation model. This model consists of the set of ellipsoids, half ellipsoids. In the foci of ellipsoids are located the receiver and transmitter. Each half ellipsoids is related to the one cluster, which is related to one delay time for the electromagnetic path. Each ellipsoid can be described by the half ellipsoid parameters. It is foci, position of the foci, and the minor diameter of ellipsoid and minor diameter of the ellipsoid. This model consists of n ellipsoids. Basing on this model, we can calculate power angular spread. Power angular spread seen in the neighborhood of the receiving antenna, this area, can be calculated using this formula. So power angular spread in the function of azimuth and elevation equals the sum of three components. First component is the average value of power angular spread for the delayed scattering components, which are related to n to each ellipsoid, half ellipsoid. Second parameter, it is average power angular spread for the local scattering components. And last one is power angular spread for the direct path component. In our simulation, this component equals 0 because in our simulation we have set the kappa parameters equals 0. This is in the neighboring of the receiving antenna. Power angular spread seen at the receiving antenna output is described by this formula. So here is receiving antenna, and the output of this receiving antenna, the power angular spread can be calculated using this formula. Of course, in the function of the azimuth and elevation, and this power angular spread equals the this value, this in the neighboring of antenna, receiving antenna pass, and multiplied by the receiving antenna power pattern, which is the function of the azimuth and elevation and half power bandwidth of antenna and receiving angle. The last equation is the basis for evaluating the impact of transmitter and receiver antenna radiation patterns on power angular spread at the output of receiving antenna. The analysis of the obtained results is based on power angular spread charts and the RMS angle spread calculation, which is defined as. So we can define angular spread using this formula in elevation and in azimuth. Sorry, azimuth and elevation. This component, it is standard deviation. These parameters can be calculated using this formula. This formula comes from standard deviation definition. We have made several simulations according to this algorithm. The first step of algorithm is the determination of the half ellipsoid parameters, which consist of the multi-elliptical propagation model. The second step is generation of the directions of the departure propagation path for the coordinate origin located in the transmitter position. The third step is calculation of the scattering point located on the half ellipsoid surface and the radius to this point in spherical coordinates. The next step is transformation of the coordinate origin from transmitter position to receiver position. The next is calculation of the directions of arrival path for the coordinate origin in receiver position. Based on the von Mises distribution, generation of the directions of arrival propagation paths for local scattering components in receiver position. For each propagation path and for each half ellipsoid, generation of the power value based on the uniform distribution and the local maxima of power delay profile. For each propagation path, calculation of the power at the output of the receiving antenna as the product of the path power and antenna power pattern. We have made the simulation. The assumptions for the simulation are presented here. We have made simulation for 38 gigahertz carrier frequency. The distance between the transmitter and receiver position was 120 meters. We have made simulation for non-light of sight conditions. Kappa of rise factor equals 0, so no direct path. And we have made propagation for two scenarios. Scenario 1, where transmitting antenna, receiving antenna were the same, so the how power bandwidth of transmitter, how power bandwidth of receiver equals 8 degrees, and antenna gain of transmitter as receiver equals 25 dB. And second, it is narrow antenna bandwidth, beam antennas, and configuration 2, different transmitting and receiving antenna, and this is a wide beam antenna for receiver, 50 degrees. Power delay profile we have taken from this paper, from literature. Here are presented the antenna pattern from the receiving antenna. We have made calculation for 4 angles. This is narrow antenna bandwidth and wide beam antenna. And we have calculated power angular spread. You can see that angular spread for narrow beam antenna is not, we can see here, not difference to the antenna pattern of receiving antenna. But we have a big difference between the power angular spread and the antenna pattern of receiving antenna for the wide beam antenna. In elevation plane is the same, and we have used the angular dispersion parameter as a sigma. Sigma is the standard deviation, angular spread standard deviation, and in the function of received angle, we can see that for narrow bandwidth antenna, there is no influence of spread, and for wide bandwidth antenna, we can see big difference in comparison to the narrow antenna bandwidth. Yes. This characteristic azimuth plane and elevation plane. We have made simulation for different environment scenario: long delay profile, normal delay profile, short delay profile, in azimuth plane and elevation plane, but only for wideband antenna. This is only for wide beam antenna. Conclusions. The obtained results shows a quantitative assessment of the impact of direction, bandwidth, and indirectly gain of antenna patterns and the environment type and the angular dispersion. For directional antenna, the angular spread is independent of the pattern, direction, and environment impact, what is consistent with the empirical measurement. The development method, which considers the influence of the antenna parameters and environment, gives the opportunity to evaluate conditions of compatible operating of 5G system components. Thank you very much.
Okay, any question? Yes.
I would like to ask about the scope of application of that models, including how about moving transmitter and receiver? Is it only static?
Only static, because this first step of our research. Maybe in the future we will. The next step for us is to, because the power delay profile we have taken from the literature, we are going to measure this characteristic power delay profile and use it for this model.
And did you consider it in any way depolarization effects due to scattering or?
No yet. No yet.
But interesting.
This is the environment for simulation is MATLAB. We have used MATLAB.
Thanks.
I have a question. You have chosen frequency equal to 38 gigahertz for your model. What if frequency is below 10 gigahertz? It means why have you chosen 38 gigahertz?
We have choose this frequency because this is the bandwidth of 5G generation. The answer is I don't know. I have to make simulation. I suppose that the results will be similar.
Because at this frequency we are going to have very high path losses means at 38 gigahertz.
I don't know. I have to calculate. This for me it is one moment because we have already we have to change only the frequency.
Any other question? Oh, okay, thank you very much.
Thank you.
Okay, the last speaker is Mahadi Hassan Ziko. The title of his speech is Optimum Electromagnetic Modeling for RF MEMS Switches. Could you copy the
Okay.
first?
Where is it?
6A. Yes. You have 15 minutes, including question section.
Hello, good morning. My name is Mehdi Hassan, and I am from Tallinn Technical University of Estonia. My topic is optimum electromagnetic modeling of RF switches. So I'm going through the short introductions with motivation, and I will discuss about applications and goal of this work, and I will give some analysis based on the method, and also I will discuss about electromagnetic modeling and its performance analysis by using the RF CAT algorithm, and finally I will give a short summary. So RF MEMS switch, here we can see that some kind of switches that is based on electromagnetic switch or piezoelectric switch and also electrostatic switch. So with this the switch, we have also need to integrate with the transmission line. So this study is basically integration with the switch, RF switch with the transmission line. This transmission line is microstrip transmission line. So the RF switch is used in a satellites or wireless and mobile phone communications. So our intentions of this study is to get low loss and getting high isolation, and so that we can use in types of like mobile phone or satellite communication. The intention of integration with the microstrip transmission line rather than other transmission line is because microstrip transmission line have a lightweight, easy to fabrications, and also it's having the modest gap where we can get the high isolations. And also the microstrip transmission lines can also easily to integrate with the CMOS process. So basically this microstrip transmission line with RF MEMS switch used in telecommunications, automations, and also military and or aerospace applications. The goal is need a low voltage. So the low voltage is already achieved. Our low voltage is 2 volt for this aluminum nitride based RF switches is already presented in other papers, and also we need to finding out for the fabrications. This paper is basically focusing on the losses, RF losses. So modeling of RF electromagnetic modeling is very important for designing of a geometrical design for actuation voltage, and because we have to compromise with the actuation voltage and the losses. That's why we have to design in a proper way of geometrical of transmission line. So basically during the integration with switch and microstrip transmission line, we have some interconnection metal loss and dielectric loss in the substrates. I mean that in the grounds, in the substrates and the insulating layer. So we need to analyze the electromagnetic modeling in this case, and also we have problem with the coupling to ground. That's why you need to investigate further in an analytical way and also in the electromagnetic simulations. So for getting the optimum design, we need to follow some certain rules, like low characteristics impedance should be between 2 to 100 ohm, and width and height ratio should be below 10, and also we have to find out the minimum effective relative permittivity, and also that is a very important, we have to follow the skin depth and also the gap size to maintain the losses as well as to minimize the voltage. So as the strips with and on the characteristics impedance and their relationships are shown it in here. So we can see that as the width is increased, the characteristics impedance is exponentially decreased, and but we have the rules that the ratio cannot be more than 10, and for a better optimizations of our MEMS in literature should not be maximum, should not be less than 20 ohm. So that's why we are choosing the width of the strip is 150 micrometers. Here we can see that is less than 10, and is characteristics impedance is around 20 ohm. For getting this one, this characteristics impedance, I go through the effective dielectric constants by range of frequencies, and also the skin depth. So this is the actual device. This device is with the aluminum. So this is actuation with the piezoelectric principle. That's why we have around 2 volt or 1.5 volts to get the actuations with the contact force of 350 micronewton, which is good enough for the alpha MEMS switches. And in this case, while using the integrating with the microstrip transmission line, we have to also consider the overlap length and also width, and also this conductor line. As we are seeing that there is a gap, this one is chosen because to get the high isolations, so that we are going to use microstrip discontinuity transmission line. So for better understandings, we need to analyze the lump element in terms of lump elements. So that's why we need to equivalent get the equivalent circuit. So here we can see that in the off states we have a microwave resistance with the gap capacitance, and this C3 and C3 is in here between this, and this C2 is the gap capacitance between the switch and the conductors. So because in high frequency analysis the current crowding is most of in this part, so we need to investigate in a proper way for better results. So in the on states, this C1 and C2, sorry, C1 is replaced with the contact resistance, and then we can find out with some kind of analytical equations by using the method. I use the total resistance and also find out the gap with the series capacitance. So this series capacitance is very important to maintain the gaps. So for this study we used the gap of 4 micrometer. For finding out the RF performance, we need to find out the scattering parameters. So I use this kind of formula and use 2D port network so that we can get some insertions and isolation loss. So the insertion loss the figure, I don't know how it's but it's not coming. So I got some better insertion loss and isolation loss. This insertion loss is because of absorptions and reflections. Reflections is because of the impedance mismatch and the resistive and dielectric losses, and the isolation loss is high resistivity of silicon substrates. From the literature, insertion loss should be like 0.001 is 1 dB is the optimum for the 50 gigahertz of RF switches. That's but in my study, why the figures don't come, I don't know. Anyway, in my study of insertion loss, I got the results is around 0.001 to 0.005. So this is good enough, and it means that is high isolations for 40 micrometer of width, and also for isolations I got the 50 dB for microstrip discontinuity transmission line, and 20 dB is the sufficient for the electromagnetic modeling of microstrip discontinuity transmission line. Here I get some literature reviews along with my research comparisons. So here we can see that my isolations losses is 50 dB and insertion loss is around 0.01 to 0.05, which is I mean that comparable with other research researcher like bridge types in terms of electrostatics, and also some series type RF MEMS switches. So the conclusion is the study of electromagnetic modeling of RF MEMS switch with microstrip transmission lines is studied based on the analytical model, and also with, for the scattering parameters. There's a study for the RF MEMS switch insertion loss is 0.01 to 0.05 dB for 50 gigahertz frequency. Moreover, there is a isolation loss of 50 dB for 50 gigahertz frequency, and for this study, slow insertions and high isolation loss is achieved for single beam series type RF MEMS switches with a microstrip discontinuity transmission line. So I acknowledge the Estonian Research Council for this study support, and also this is the reference, and thank you for your attention.
Thank you. Any question, comment, contribution? No? Okay, thank you very much. So this morning we have listened 6 presentations. I thank all of your great presentations, and also I thank you all of you for attending this session and this conference. Thank you very much. The next session will start at 11. So after 10 minutes we have a coffee break. Thank you very much.